All right, the figure shown in 29-2, L equals 4 henries, R equals 6 ohms. The voltage is 48 volts. What is a self-induced EMF of 0.5 seconds after the switch is closed? Okay, so let me back up and make sure I know what circuit figure number 29-2 is. All right, so this looks like the circuit we're talking about. I assume we're talking about closing switch 1 because closing switch 2 would do nothing. So switch 1. So basically that middle wire is basically useless to us because the switch is open and therefore not doing anything. So this is a simple LR circuit. That said, self-induced EMF. What is self-induced? That means that the inductor, what is the inductor doing? Well, the inductor is resisting change, right? So it's going to resist the battery. Initially, it starts high, stopping any current going through that wire initially. And then as time goes on, it becomes zero. So it is a decreasing situation, correct? It's a decreasing situation. We know how to deal with that because we have the formula. Decreasing is going to be V max. E to the negative t over tau. We know tau is going to be equal to L over R. The L is 4, the R is 6. So I'm going to get 2/3, which since I'm putting on the bottom, I'm going to flip and multiply because I don't like having tau on the bottom to begin with. V max, what's the V max? At the very beginning, this thing's going to stop all current. So if this thing's pushed, this battery's got 45 volts, what's the inducer doing? It's pushing back the other way at 48 volts. So the maximum it could have is 48 volts. E to the, remember I'm flipping this, so -3/2 times T. So there's my formula for the voltage down the road. Since that's the formula for the voltage down the road, all I have to do is plug in my time. V equals 48, E to the -3/2 times 0.5. So that is -3/4. Whoop. I do an E to the, and I get 0.47236 blah, 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 times 48. And I get the voltage of it. A whole half second later, it's already given up to the point where it's a resisting change just exactly that much. And that is how you do number 5 on this worksheet. Okay, so again, what's happening? It's an LR circuit. LR circuit, the voltage is going to be maximum at the very beginning, which means it's going to decrease, which means I use a decreasing formula, which is X equals X max, or in this case V, because we're talking about voltage, equals voltage max, E to the -t over tau. Tau is calculated by doing L over R. I get 2/3. Okay, I then plunk it all in the equation. I recognize the maximum voltage is going to be when this thing shuts down the circuit, which is at the very beginning, which is when it had 48 volts. It's going to have to push 48 volts the other way. In doing so, that means the maximum voltage it's ever going to have is 48 volts, it being the inductor. The inductor is what stops the flow of charge. Therefore, it has to have a back voltage. And that's what it must be talking about. It says self-induced EMF, although it would be nicer if it was just a smidge clearer, right? That the self-induced voltage, it can't be the resistor. Resistors don't have voltage. They don't act like batteries, but inductors do. So that must be what they're talking about. All right. So I'm going to get the next one ready. The circuit figure 29.21. What energy is stored in the inductor when the current reaches an equilibrium value as which is closed? Okay, so on your formula sheet as well as on on your notes, you have the following formula for energy of an inductor. Energy of an inductor is equal to 1/2 Li squared. So all I need is my current, and they want to know once it reaches equilibrium. When it reaches equilibrium is when the inductor has stopped yelling, "Get off my lawn! Get off my lawn!" So because of that, once it stopped yelling, "Get off my lawn, get off my lawn," pretty much the inductor is sitting there watching the current go by and not bothering at all, which means V equals IR. Voltage is 24. I is equal to, I don't know, my resistance equal to 8. So I get a current of 3 amps. Once I have that my current is 3 amps, this should be child's play. The amount of energy stored in it that it can use up later is going to be L 4 3 squared, and I get 6 And the unit for energy is joules. Did I do that right? I did not do that right. I didn't square it at all. That's wrong. So let's change this to 18 and make my life better. All right. How about 18 joules? That's 9 times 4. 3 times 3 is 9. 9 times 4 is 36. And 1/2 of that is 18. So straightforward consideration. Look at the circuit. It says equilibrium. It reaches equal. When you first throw a switch, the inductor is saying, no, not go on. You can't move here. So it shuts down the circuit. But slowly, as we already talked about, the inductance cannot stop the flow of current. It slows it down. It fights it with it the whole entire time. So initially, it has a voltage of 24 volts. Sometime in the dim and distant future, it basically says, yeah, I like having kids on the lawn. I like watching the current go through the wire. I'm perfectly happy with that. In fact, if you cut off that, it would start fighting the other way, start running current back through the resistor the other way, right? And so therefore, right now, looking at this circuit, it would say, initially, it's fighting it. The current's constantly changing. At some time in the dim and distant future, though, the inductor's doing nothing, so the current eventually gets up to the 3 amps it's supposed to get up to, right? Once it's at 3 amps, how much energy can the inductor store? The formula for it is 1/2 Li squared, and that's it. That's all it takes to solve this problem. Again, if nothing's helpful, let me know. I will zoom or